Okay, but to kick things off, we are going to finish off where we left off on ideal gas mixing properties. So ideal gases are the simplest fluids that we can handle. So this is why we always start off with the ideal gas mixtures. So before we showed that the internal energy of an ideal gas mixture, right? So the U over bar corresponds to the internal energy of species I as it is in the mixture. Since it's ideal, this is exactly the same as how it would behave as just a pure ideal gas. So a couple of the superscripts that we'll be using for approximations here. IgM is the ideal gas mixture. We'll have Ig, this is ideal gas. So some of these are redundant, right? If you're recognizing that if it's an ideal gas, it's not interacting, then you should know that the ideal gas and ideal gas mixtures are the same thing. For U, V, and H that works, but for entropy we'll see that's a bit different. Oftentimes we'll also say IM, which is an ideal mixture. And I think we'll cover that one towards the end of the class. But these are some simplifying approximations. Okay, so, but what we're going to talk about now is entropy of mixing. So we are going to construct another arbitrary system of sides A and B. So we have N of A, T of A, P of A, N of B, T of B, P of B. To make things simpler, we're not going to be changing the temperature or the pressure, which is exactly how we've defined our partial properties. So we're going to say that TA equals TB equals T, PA equals PB equals P. And again, the system is going to be completely isolated. It's going to be closed. So the only thing that's happening in this particular system is that we are going to take this membrane here and we are going to get rid of it and allow the two chambers to mix together. No temperature changes, no pressure changes, just we're going to allow it to mix together. So I guess in this sense, well, it's an ideal gas, so there's not going to be any enthalpy of mixing. But if this were a real fluid, I guess we couldn't have the system be completely isolated because it might be an endothermic mixing or an exothermic mixing. But we're going to do it isothermally. But since it's an ideal gas, it doesn't matter. Okay, so what we're trying to get here is what is the entropy change of mixing. So ultimately what we're looking at is what is the entropy at the initial state versus the entropy at the final state. So delta S of mixing is equal to the S final minus the S initial. So we'll swing back around to that to come up with a formula for the delta S of mixing, but let's just talk right now about the delta S of this whole system. All right, so this is A and B chambers. This is going to be equal to the delta S of all the material inside A. And we could label these, molecule A and molecule B. They'd have to be labeled as such. Plus the delta S of B. Now, if we go back to sort of the state change calculations that we were doing before we started working into the multi-component systems, remember that the delta S of an ideal gas is going to be the integral of 1 over T du plus P over T dV. we write this as C sub V over T dt plus P over T dV. So this term here is going to go to 0 because we're saying we're keeping the temperature constant during this mixing process. Right, but the volume of the gas is changing. So effectively, how we're going to do this calculation is we're going to allow A to expand into B and B to expand into A. They're totally non-interacting systems, and it's symmetric, so everything that we'll do for A is effectively exactly the same for B. But they don't feel each other, so it's like two independent expansions going on simultaneously. So it's some magical barrier that just is impervious to one but not the other. So we're going to crunch through all of this just looking at delta S of A, but then we'll know that just swap A and B and it's exactly the same thing. So delta S of A is going to be equal to the integral of P of A over T dV A. If we substitute in the ideal gas law, we can write this as NART over V of A. So this, of course, here is just P from the ideal gas law, rather P of A. Get rid of these temperatures. The N and the R's go outside. NA is constant. R is always constant. This is an integral that seems to pop up all the time, every time we deal with entropy. A little bit of rearrangement then. So in this last step here, recall that if we flip, take the reciprocal inside the log, it's just the negative of the log, just log properties there. Okay, so we're going to recombine this, right? So this is delta S of A, exactly the same procedure for B, so we're just going to reassemble that bit there. So we have that the delta S of the system as a result of the mixing process is going to be, yep, go ahead.
So you said the delta B is equal to delta, the change of volume B is not negative of volume A, right? Because it's not, the increase of one doesn't increase the other one.
One more time, say that again.
Yeah, the volume of B is not the negative of the volume of A, the increase of volume B.
No, correct, right. It is not, good question, okay. So the question was, is dVA equal to minus dVB, effectively, mathematically speaking. And so that was sort of the case when we were talking about this type of a system for the equilibrium criteria, right? Because remember, in that circumstance, we could have a little bit of molecules of A moving to this side and a little bit of molecules B moving to that side to check if we're in equilibrium. This is not the case. So if this barrier either squished this way or squished this way and was impervious, then this would be true. But in this case, no. We have some magical barrier where A can expand this way and then B can expand this way at simultaneous, because we're effectively mixing these two things, but we're controlling how the mixing is occurring, because we don't care about sort of the process, we care about the end states, right? Because this is a state change. So we can kind of arbitrarily define our system. So this is not the case. So both volumes are expanding simultaneously. Okay, so one other quick thing before I write this down, actually. So what we're going to say is that V of A2 is going to be equal to V of B2, meaning that A and B are expanding into exactly the same final volume. We are going to call that just V. We can also write this by substituting back in the ideal gas law. This is nRT over P, which is equal to summation of NIRT over P. This is basically manipulations of the ideal gas law. Okay, so if I move the NA and the NB sort of over to the left-hand side of the equation, we can get delta S underbar is equal to minus R ln of V sorry, no, this is no underbar here. And we've got one more manipulation before we get to our final result. So VA1 over V, we can rewrite this as N of A RT over P over the summation of N of I RT over P. All the stuff cancels out except for N A over summation of N of I, which is just equal to X of A, which is the mole fraction of A. And likewise, same thing for B. Right, so that we have that V, B1 over V is equal to X of B. Okay, so our result, when we put everything together, is that the delta S of the system, which is the same thing as the delta S of the mixing, is equal to the S of the final state minus the S of the initial state, which we're going to say is NAS underbar of A plus NB S underbar of B. This is equal to, looks like I got to update my notes. I'm whipping around NAs and Bs left and right. I pulled it out this time. Notice that there's no underbar there. So we can also write that the S final is equal to the summation of n of I s over bar of I. So if we divide by n, which is equal to NA plus NB, effectively just many different ways to write more or less the same expression. But we will generalize the bottom equation in just a second.
Can we group logs together too, and then?
Generally, it's not what's done. So if everyone's mostly got everything written down, I'll move to the next slide. So our final result is that we can write that S over bar of I, so this is the entropy in the mixture, is equal to S under bar of I minus R ln of xi, and that the delta S of an ideal gas mixture is equal to minus R summation xi ln of xi. So even for an ideal gas, we have the relationship that we saw with U, H, and V doesn't hold true anymore, right? Gases, even if they're ideal, right, you cannot just say they behave exactly the same in a mixture as they do as a pure component, because you gain entropy as a result of the mixing process. So if we look at this, we say that x of I is always less than 1. It just has to be by definition. So that the ln of xi is always less than 0. So that the negative ln of xi is greater than 0. Therefore, the delta S of mixing is greater than 0 always, and that the entropy of a species in a mixture is always greater than the entropy of the species as it is alone. Because at a minimum, even for an ideal gas, effectively what we're doing is we're increasing the volume of that particular ideal gas. As you increase the volume of something, it's got more room to move around in, and so then sort of conceptually that means we should have a greater entropy of the system as well. But entropy causes a lot of heartache when it comes to phase equilibrium, and that's why essentially we have to use excess properties. Okay, so a couple other really quick things. Anything else that has entropy in it is going to have something of this kind of funky form, this ln of xi type thing. Now, one of the problems, right, is that xi, so what's the natural log of 0? Exactly. So that's kind of a problem. So if you ever wanted to look at dilute mixtures, right, how does a system behave as xi goes to 0? You are approaching a discontinuity. So we need to define something, fugacity, that allows us to avoid that discontinuity. So excess properties and partial fugacity are designed to avoid this discontinuity here. Right? So in reality, if you're ever looking at the phase behavior of a dilute system, you in essence have to take the limit as xi goes to 0, because xi at 0 is undefined. Right? You've got 0 and negative infinity. I don't really know how to evaluate that too well. Right? So you always have to take the limit of what's going on here. So anyway, so if we were to write out for Gibbs, right, delta G is defined as delta H minus T delta S. Right, the enthalpy term here we don't have to worry about too much for an ideal gas system, right, because we know that the delta H of mixing for an ideal gas is 0. But if we're dealing with the entropy term, the delta G of ideal gas mixing is equal to the summation, let me write this different, is RT times the summation of xi ln of xi. So we'll notice, one other thing before I go into a story about that. G over bar of I for an ideal gas mixture is equal to G under bar of I plus RT ln of xi. Okay, so a couple of key properties looking at this. Just as when you give, so in the entropy term, you have a negative term there, which means that all the negative values for the natural log flip to positive, so your entropy always goes up. But in the Gibbs free energy, right, it's a positive term here, which means that when you mix, the Gibbs always goes down. Always. So in essence, phase behavior is a balance between the gain in entropy that you get when you mix two things together versus the penalty of mixing two things that don't want to be in contact with one another. So if you're trying to figure out if two things are going to be miscible, the main thing to look at is what is the relative contribution from entropy, which is always going to be encouraging mixing, versus the penalty from enthalpy of mixing. So if you mix two things together and it's exothermic, then you're almost guaranteed they're almost going to be infinitely miscible, unless you get to a region when you mix them and they're endothermic. Now, if you mix two things that are endothermic, that doesn't mean that they're not going to be miscible necessarily. It just has to be that the degree to which they're endothermic cannot overcome this contribution from the entropy of mixing, is essentially what's going on. Now, there's a couple of other properties here, I think we'll talk about later on, but this function for the entropy of mixing, right, you effectively gain an infinite amount of entropy. If I were to take one molecule of A and toss it into a sea of B, those systems have to be miscible. It is not possible not to be miscible, because what I've done, because all of our calculations in phase equilibrium, we're assuming infinitely sized systems, right? Or effectively large enough that you don't have surface tension effects, you don't see walls, you don't see boundaries, right? And molecules are so very, 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 very small. So if I put one molecule in this room, right, it's effectively an infinite area for that molecule to move around in. What this equation is saying here, right, is that if I put in x of I is equal to effectively 0, right? That means I am gaining effectively an infinite amount of entropy to that particular compound. There is no amount of unhappiness from that molecule based on its surroundings that will prevent the entropy from dominating. So what this term here basically represents, the one that's circled up top in orange, what this term represents is basically a fundamental statement highlighting that everything must be miscible in everything else to some degree or extent. Always. And the analogy I always like to give is they say, oh, it's like oil and water. Oil and water don't mix. Well, oil and water do mix to a small extent. So the analogy that I always give is, so I do a lot of oil and gas research in my group. So if I were to take 50-50 mixture of crude oil and water and shake it up and then draw the water out and put it in a glass, who here would want to drink it? No one. Right? Because there's always, well, maybe some people would want to drink it. I hope not. But basically the gist of it is that no matter what, there is going to be some compound in that oil, regardless of how hydrophobic it is, that is always going to dissolve into it. Likewise, there's always going to be some water in that crude oil. And actually that water in the crude oil causes a lot of corrosion issues in the refinery. So there's companies that are very interested in lowering that. But the basic thermodynamics from this right here is that everything is miscible in everything else to a small extent. And that gases are always miscible because the density of them is so low that the penalty of mixing is never overcome based on the entropy. Okay, so what we're going to do is go back to the sheet that I handed out and kind of just rattle off a lot of these equations. So we could go through the process, but basically, we could expand dg with respect to t, p, and ni. And there's a neat little trick that we can do with the Maxwell relations where the order of the derivative doesn't matter. So this definition here, hopefully this is something that should be somewhat familiar because we derived it in class and you guys worked on it in the homework. Right? This is basically just a thermodynamic identity with a little trick thrown onto it. Right? These have overbars on top, whereas when we worked with it, it didn't have an overbar. But we can swap the order of the derivative. So what we can say is that S overbar of I is equal to ds dni at constant t, p, n, j not equal to I, that long thing. So what we can say then also is that this is actually equal to d dni of minus dg dt, which in this case here is equal to S. So the cool thing about the way that we sort of structured the partial molar properties is it just happens to work out that you can just draw an overbar over basically anything, right? And it still gives you exactly the same identities, exactly the same Maxwell relations, exactly the same definitions of Gibbs and Helmholtz and enthalpy and everything like that. So what we're going to do then is when we first defined fugacity, we took advantage of this property right here, that the change in volume going from basically pressure equals 0 to some pressure, right, that is related to the Gibbs free energy. And that's how we basically define the fugacity. So in the next equation here, so at a constant temperature, going from P1 to P2, right, constant temperature, which means this entropy term goes away in our expansion of Gibbs. We're only left with this expression here. So we're going to Gibbs of the mixture at some constant temperature to P2 all the way from P1, same temperature, same composition, right? We're just integrating this partial derivative down there. then effectively we just decided, hey, this makes a lot of sense. Let's just do it this way. If we say that P1 is equal to 0, that means that P1 at state 1 is an ideal gas state. So then we just define the partial fugacity of a mixture as this big, long equation here. So this far left term, this is effectively just the definition of fugacity that we have chosen to be convenient. The middle term is saying we are counting the fugacity as the deviation between the real fluid properties Gibbs, this term right here, and how it would behave as an ideal gas in the mixture. And this is exceptionally convenient because we have avoided now that discontinuity in the ideal gas mixing entropy. We're no longer considering what is the true Gibbs. We're saying what is the deviation of the Gibbs from the ideal gas Gibbs. So the whole point of fugacity is exactly right here in what we talked about. It is the entropy of mixing that ruins everything and forces us to add on an extra layer of nomenclature and tediousness to thermodynamics. But if it was not for the discontinuity in the entropy of mixing, fugacity would not exist. That is the sole reason why fugacity exists. Because it is so much easier to just forget about that discontinuity and say, look, ideal gas calculations are relatively trivial. So what we're going to concern ourselves with is the deviation from ideal gas behavior, because that's how we can more easily deconstruct and reconstruct tables of information. Because it wouldn't be very pleasant if every equation had a summation of xi ln of xi. Right? It's much easier if you have a much more simple, compact expression. And then the far right term here, right, this is basically just the evaluation of that integral going from the ideal gas state of P equals 0 to some real fluid state of P. How does the material behave in the mixture versus how would it behave in the ideal gas mixture? Right, and this term right here is where we contain all of the annoying xi ln of xi kind of business. And so the end result that what we care about here is this partial fugacity. It has that factored away. It's been removed. So here we have the fugacity coefficient. At low pressures, we can assume that the vapor phase is an ideal gas phase, and everything simplifies down that the fugacity is simply the partial pressure. And then we have a whole slew of other ways, and this is all in the sheet that I handed out, and I'll post it to Canvas as well. We have a whole slew of other different ways that we can write these expressions. Right, this one here is basically saying how does it behave in the mixture versus how does it behave as a pure component. So you'll notice the one thing that's different here is that this is no longer the pressure, it's the fugacity of the pure species. So maybe this is the easier way to do it. Because if it's trivial to calculate the real fluid behavior from an equation of state, then maybe this is the best starting point. If you want to change the composition of the system, basically at constant temperature and pressure and just mixing, an expression there. Our equilibrium criteria is that the partial fugacities have to be held constant. And the last really big heavy hitter here is how would we calculate this from an equation of state. So far, everything looks pretty reasonable. This is the ideal gas specific, or ideal gas properties. Question? No, okay. So in this case here, we've transformed out from dP into dV units, so that we have a switch of things going around. That's where this Z comes from again. So this term right here corresponds to the property of the ideal gas pressure. Now this variable right here is the tricky one that we have to evaluate. So in an equation of state, it's typically pressure is equal to a function of volume, temperature, maybe the number of moles, but in this case now it has to be the number of moles of each species. So the tricky part evaluating this partial fugacity expression to use an equation of state to do multi-component phase equilibrium calculations, we now need to add in some new way so that the equation of state knows or it cares whether or not I'm adding component 1 to the system, or component 2 to the system, or component 3 to the system. So that comes down to a term called mixing rules. And basically, what that means is, how do I calculate A and B and omega for that particular equation of state when there's lots of different things all mixed together within it? And I don't want to ruin the fun, but basically no one knows how to do that very well. So mixing rules, to a large extent, are empirically derived. The equations of state, again, I don't want to ruin the surprise, but they're empirically derived as well. The foundation and the structure of those, they've got a pretty good head start, right? The van der Waals equation seems to capture some real physical behaviors of the system, saying, okay, well, we'll say this B term is the excluded volume. Okay, we'll say this A term is how these molecules interact. But when it comes down to the real details of it, they just fit it. They just say, okay, this is a big complex form, and it seems to fit the data really well, so what do we care? Same thing when it comes to mixing rules, right? It's a very complex system, and this is a problem that we haven't solved across any scientific disciplines, for example. So let's say, for example, we're using macroscopic continuum thermodynamics, right? The terms, internal energy, enthalpy, Gibbs free energy, these are just artificially constructed functions and variables that make our calculations easier. Let's say we're really good at it, okay? Let's say we're going back and we're going down to the molecular level, and I'm going to define how molecule A interacts with molecule B, right? And there's groups of researchers that do this, right? It's called molecular simulations. But the downside is that they also have to make these simple assumptions, right? All molecular simulations, almost all of them, probably 99.9% of them, assume pairwise additivity. So what they basically say is not that there's any three-body interactions, right? You know, they say the three-body problem in sort of physics, right, where you can't, well, you can, for very specific circumstances, you can analytically solve Newton's laws of motion for 3 rotating bodies around an orbit, right? That's like this grand problem in physics. And people have solved it for very, very specific circumstances of rotations and masses and things like that. But for molecules, right, 1 mole is 10 to the 22, 10 to the 23 molecules, right? So if I'm an atom, I'm surrounded by effectively a countless number of other atoms nearby. But all simulations say, no, that's too complex. I'm going to say atom 1 interacts with atom 2, and then atom 3, and then atom 4, and then atom 5. And then I add up all those factors together, and then voila, that's my net interaction between all those different molecules. Right? So even if you think you're diving in super deep to all the details, most all of our calculations are still dependent on a few basic assumptions. So hopefully that lessens the blow that all this is empirically derived. So with thermo, effectively what we're doing is we're laying the groundwork to organize and categorize information and how to deconstruct it or depack it. And so that's where things like excess properties, partial fugacity, and all this other fun stuff, right? So we spend a lot of time and effort deriving these beautiful, elegant equations, but then they're so complex and we don't have accurate enough data that we have to start to empirically break it down. So we didn't have a chance to get to excess properties today, but we'll talk about that. Oh, I guess it has to be next week, unfortunately. So we'll talk about excess properties and activity coefficients and things like that starting next week. But then once we do that, then we're basically on to vapor-liquid equilibrium. And we can start actually doing some real application systems. But exam on Friday, review on Wednesday, so please bring questions. I'll post the solutions to the practice exam today after class, but please do take the exam sort of blind, right? You've got the equation sheet and a calculator, and that is all you will have access to. For the exam, no cell phone calculators. Only, I don't know, real calculators? Something that's like a TI or something like that, right? Just something reasonable. And that's what we'll use. Okay, any other questions about that? Okay, have a good week.